of different cases of functions. I think the best way for you to understand this topic is still following the uniform we were talking about. Okay, so this is the uniform way. Every time you look at a function, you want to see the graph, or you want to graph the function yourself. Always begin from this information. Okay, that's a very good question. Any other questions you want to ask? So this is what
Yeah.
okay. So that means I have to worry a little bit about my appearance every time. Anyway, thank you for the work. Okay, so I think this class is this lecture is going to be very very fun. So we're going to talk about section 13.3, unit and continuity. So we're still on z is equal to s. Two independent variables x and y and one independent variable z. So in last week we talked about several different topics, domain of the function. So one of the most important things I want you to remember is the domain of a function involving two variables should be region in R2, right? It should be a region in R2. This is probably the only new thing you learn. So region in R2. In order to find the domain of the function, you look at the formula defining the function and use the restrictions. Right? So the restrictions coming from fraction, coming from log, coming from square root, coming from in rare cases arc, cosine function, or sine function, or some other functions. Arctan function doesn't have any restrictions, so etc. For instance, if you see a log, then what is inside has to be strictly positive, right? So these restrictions are coming from these different functions, and then you divide what the domain is. The range takes a little bit more effort. The range is an interval or a union of several intervals in R1. Okay? So in order to see what the range is, you need to take advantage of the statistics formula. That squares, number one thing that jumps into your mind is the squares have to be then negative. And so that a square, x squared is always negative. So you have to take advantage of this kind of information in your formula. Okay? We also talk about graph. The graph of a function, if you have two independent variables, is a surface in R3. Okay? So in terms of surfaces, we have introduced several different types. We have introduced planes. So the planes are coming from the formula where you only have linear terms. So if your formula only have linear term, first order term, no squares, no x times y, no xy squared, it has to be a plane. We also talk about chordic surfaces. These surfaces are coming from if you have a second order term, x squared, y squared, z squared, or xy, yz, this kind of second order term. Okay? And there are some other type of surfaces as Emmanuel was asking about. Sometimes if you have restrictions on a domain, you don't have the full surface of the plane, you don't have the full surface of a quadratic surface, so they are restricted to the domain. So there might be pieces of planes or quadratic surfaces. Right? So a perfect example we have is z is equal to square root of x squared plus y squared. So this is the example we look at in last week. This one can be easily transformed into a very nice function. Right? So you can square both sides and move terms around. You can find this is actually a cone. All right? This actually is a cone. So it's x squared level curves, which are a union of curves staying in the xy plane. So they are coming from fxy is equal to k for different values of levels. So you're choosing different values of k, you're getting a family of curves on xy plane. So combining them together, this is going to be called a contour map. So contour map is not exactly a graph of a function, but it is a very useful visualization of a function. It's like you have a surface, and then you're cutting off the surface at different levels. Every level you're cutting the surface, you're getting a curve, and then you're mapping all the curves back onto the xy plane. And this is going to be the contour map. You can still recover a lot of the information about these curves. Okay, how to recover, how to build. This is not the key issue from this class. Okay, the key issue from this class is how to compute and how to get the information involving the formula. You can read the book and see what the contour map is telling you. Okay. So today we're going to talk about the limits and continuity of a function. So first I want to give you the definition. Limits. So limits and continuation are the only remaining topics before we introduce derivatives and integration. Okay? So limits of a function are a pointwise behavior. So first of all, I want to mention this is a pointwise property of z equals f(x1). What I mean by pointwise behavior, it means in order to talk about the limit, you're going to have to have a function, and then you're going to have to fix a point. Okay? You have to fix a point, and then you can talk about the limits of a function at a fixed point. For instance, you can fix a point AB in R2. Okay? So we'll fix a point in R2 in the very beginning. Then we will talk about the limit of a function when the neighboring points are approaching this fixed point. The function value will be approaching to a fixed value L. So this will be the notation for a function to have a limit equals L when xy approaches a fixed point AB. This is what I mean by pointwise property. So a limit of a function has to be pointwise behavior. So you have to have a point in order to talk about what a limit is. Okay? So if a limit of a function when xy approaches AB is equal to L if for any given epsilon greater than 0, there exists delta greater than 0 such that if the difference between these points is greater than 0 and less than delta, then the function value difference is less than epsilon. Okay? Have you seen this kind of epsilon dot line before? You probably heard about that, right? In Calc 1, you probably also define limit of a function, but in that case, you only have one independent variable. But the language is pretty similar. Okay? Again, in this class, we're not concentrating on concepts. Okay? So I will introduce the concept, but more importantly, how do we use this concept to computation? So when you leave this class, you don't have to remember this definition, but you have to know what a limit is and how to compute a limit. Are you with me? You don't have to remember what the definition of a limit is, but you have to know how to compute a limit. If I give you a function and I give you a point, okay? I will give you a very brief explanation of what this epsilon dot length means. It actually means when the input is close enough to the fixed point. Okay?
It doesn't have to be the value, it just has to be within just close to the value.
The beauty of the definition is this epsilon is arbitrary. Okay? The beauty of the definition is you have to allow this epsilon to change. You have to make sure this is true for any given small value of epsilon. And so it's not a fixed distance around L. It has to be no matter how small it is close to L, you can always find this delta such that if xy is close enough to this point, then the function value will be close enough according to what you require in the very beginning.
Got it.
You know what I mean? So you can require the closeness of the function value in the very beginning, then I will give you a closeness of my input, such that as long as my input is this close, it will satisfy what you require. Okay? Only in this case, you can say this limit of a function is equal to this fixed value. Okay? Again, you don't have to be completely understanding what I'm talking about. I have one remark to make right here. Even though I'm defining a function at this fixed point AB, I don't have to require AB to be in the domain. Okay, so AB needs not be in the domain of F. Okay?
Why is that?
Okay, so yeah, that is a very natural question. Look at this condition, which is essentially saying I can define the limit of a function at a point, even if this point is not in the domain. The mystery comes from this condition. I said, as long as the function value, I'm sorry, this is a big difference. I have to require this is equal to L, otherwise it's not even purely inequality. Sorry, this is a key difference. Okay, so yeah, the function value is close enough to the function to the value I fixed in the very beginning L. Yeah, I'm sorry, this is supposed to be L. The reason I don't need to require AB to be in the domain is coming from this inequality. So I'm saying as long as xy is close enough to this fixed point, but this xy will never touch on this fixed point because of this greater than 0 condition. All right? I'm just saying as long as these neighboring points of xy are very close to the fixed point, but it is never equal to the fixed point, then the function value at this neighboring point will be close enough to this fixed value L, then you will have a limit. But in the whole process, I never require my xy to be exactly equal to this fixed point. So when I evaluate, I will evaluate my function at this xy, the neighboring points. I don't have to evaluate my function at AB at all. Are you with me? Which means I don't need this AB to be in the domain. What do we mean by AB in the domain? When we find the function, we find its value. What is the meaning of the domain of the function? You can evaluate it. Am I right? It's equivalent of saying you can evaluate the function. You can find the value of a function when you put in these 2 points A and B. Am I right? So in the domain, essentially says you can evaluate. But throughout the definition of the limit, I never did the evaluation for the function at AB. What I did is the evaluation at the neighboring points. So I can't require this, I don't need to require this point to be in the domain of the function. Okay? That's the big difference between limits and continuity. So the next one is continuity. Continuity is still a pointwise behavior. So we will say a function is continuous at a given point. So we'll say f is continuous at a given point AB, but right now I have to require AB is in the domain if the limit is exactly equal to the function value at this point. Okay, so that's the definition for continuity. So we'll say this function is continuous at a fixed point AB if the limit of this function when xy approaches AB not only exists, but also it is exactly equal to the function value at this fixed point. Then it will be defined as continuous at this fixed point. Here I do have to require this fixed point AB to be in the domain, because in this definition I actually did evaluation at this point. All right, so I have to require this AB to be in the domain. So the continuous property is a pointwise property. You can ask a function is continuous or not at fixed point. But we can also say function is continuous in a set if f is continuous at all the points in the set. Okay? A function is continuous in a set is a stronger property than continuity at a fixed point. All right? So if we're given a set, and then we can verify if function is continuous at every single point coming from the set, then we will say this function is continuous in the whole set. Again, if you feel a little bit missing and boring, don't worry about that. We're going to evaluate the limits